say many thanks to the organizers. I'm the first time in Korea and I really enjoyed it now. Thank you. So my talk is devoted to a particular case of this correspondence between combinatorics of simple polytopes, phase rings and moment-angle manifolds. Namely, I consider today the case when moment-angle manifolds are homeomorphic to a connected sum of products of spheres. And what is the combinatorics and what is the algebra of the phase rings in this case? So what is the algebraic and combinatorial approximation of this topological case? That is my point of view today. So to begin with, I would like to mention the main definitions. Of course, Nikolai Yerokhovets today gave the definition of moment-angle manifold, moment-angle complex. So let me briefly mention the moment-angle complex of a simplicial complex K on the vertex set M is a CW complex viewed as a subcomplex in a unitary disk D to M. So the simplest examples are just the disks. It's a case of a simplex. And if you have a join of simplicial complexes, then this construction behaves nicely and you obtain just a product of moment-angle complexes. Something less trivial is if you consider just three disjoint points, then moment-angle complex is homotopy equivalent to the following wedge of spheres. So next, simple polytopes. So to fix the notation, we consider simple convex and dimensional polytopes in Euclidean space. Such a polytope can be defined as about an intersection of M half spaces. And we, of course, assume that the hyperplanes defined by the corresponding equations are in general position. So most n of them meet at a single point. In this case, this point is a vertex of a polytope. And we will, of course, also assume that there are no redundant inequalities in this definition. No inequality can be removed from this definition without changing the set P. So then we have facets. We have M facets. Numbers M and N are fixed through the whole talk. And of course, we have a matrix whose rows vectors are AI. The vectors defining normals to the facets. And we consider the affine map by this matrix A and the column vector B. And this map embeds P into the non-negative orthant Rm of dimension M. And so, using this map, we can define space that P, moment-angle manifold, from the commutative diagram, just as a pullback, where mu is the moment map, and it can be thought of as a quotient map of the action of the standard torus on Cm. Therefore, torus acts on ZP with quotient P, and we have also an equivariant embedding in a complex m-dimensional space Cm. So it is proved, for example, you can see it in Buchstaber and Panov book, that P is a smooth closed two-connected manifold of dimension m plus n, and this is called moment-angle manifold corresponding to a simple polytope P. Also, the most trivial examples are, in this case, spheres and products. Namely, if you have a simplex, then you have a sphere. And it also behaves nicely if you have a product, not a join, but a product of simple polytopes now. And so the examples which are not so trivial are truncation polytopes. Let P be a truncation polytope. These are famous in combinatorial geometry polytopes, for example, used in low bound theorem, duals, so simplicial ones. This theorem gives you low bounds for phase vectors. And this is, we have delta n, we have a simplex, and we consequently cut down k of its vertices. Then, due to a result of McGovern, its reformulation, of course, from the original work, the corresponding moment-angle manifold ZP is diffeomorphic to a connected sum of products of spheres. Two spheres in each product. And we have the coefficients in this formula, the powers. These are just, of course, the Betti numbers of the moment-angle manifold. And we can see in this case, in this particular case, they do not depend on the dimension of the truncation polytope. Generalized truncation polytopes, as I call them, these are just vertex cuts of finite product of simplices of arbitrary dimensions and arbitrary number of vertex cuts. So from the results of Gittler and Lopez de Medrano, and recently there is a paper of Chinese mathematicians Chen, Fan, and Wang, we know in this case that in the case of r equal to 2, the corresponding ZP is diffeomorphic to a connected sum of products of spheres with also just 2 spheres in each product. For example, if we have now not a truncation polytope, but a one vertex cut of a product of simplices, then the resulting 17-dimensional smooth closed manifold is the following one. In this example, we see that 5th and 6th Betti numbers are equal to 0, not like in the case of truncation polytopes. So open questions are, what is the criterion for us interesting in terms of combinatorial commutative algebra of a simple polytope P to give a connected sum of sphere products with just 2 spheres in each product? But also interesting is, as far as I know, open question, is there any simple polytope that gives ZP topologically non-trivial connected sum of products of spheres but with 3 spheres in each product? At least we can have 3 spheres, just you have 3 product of 3 simplices, then ZP is, of course, product of 3 spheres, but it's trivial connected sum. And now we are going to discuss a conjectural answer to question 1. So what is the combinatorial algebraic approximation for this case? For this, let us fix a base field K and consider n-dimensional simple polytope P with m facets. So we have its boundary of the dual is a simplicial complex Kp, and we have a polynomial algebra on m variables. So the face ring, or the Stanley-Reisner ring, is the following quotient ring, quotient of a polynomial algebra over a monomial ideal Ik, which is generated by square free monomials such that the corresponding indices do not form a simplex in K. This face ring is a module over a polynomial ring because of the quotient projection. And so we can form the Tor module, or Tor algebra it will be. And the face ring is called Golod if the multiplication, cup product, and all high-MSC operations in this Tor are trivial. If so, the complex K we will also call Golod 1, because we drop the field, we fix it. For examples, you can see all skeleto of simplex, just one simplex. You can also glue 2 triangles along an edge. And more interesting is a minimal 6-vertex triangulation of RP2 is also Golod. And my result is that we can generalize example 2 as follows. If you have 2 Golod complexes, then we can glue it along a common simplex. Then K is also Golod. A minimally non-Golod property is the next step. If K itself is not Golod, but deleting any vertex from K turns the restricted complex into a Golod one, then K is called minimally non-Golod. Of course, if you drop a vertex from a Golod complex, it still remains Golod. We can see it from Buchstaber and Panov theorem, for example, later. Polygon case. What about polygons? Kp is minimally non-Golod when P is an m-gon, square, 5-gon, 6-gon, etc. And Kp is Golod when P is a 3-gon. A simplicial complex K is called flag complex if any set of its vertices pairwise joined by edges form a simplex. For example, all cubes. And m-gons, m is greater or equal than 4, but not a boundary of a simplex. So the motivation for me was the following 2 results of Elena Gorbich, Taras Panov, Stefan Terrio, and Ji Wu. First of all, Golod complex case. If K is flag and Golod, then it's equivalent to, it's combinatorial characterized, its first skeleton, so its graph is chordal. That means all induced cycles in the graph have length 3. So they are not cycles of lengths 4, 5, etc. And it's equivalent to Zk being homotopy, a wedge of spheres. And also the next result in the Flach case, which characterizes the case of minimally non-Goladness. Kp is minimally non-Golad if and only if Zp is homomorphic to a connected sum of sphere products with exactly 2 spheres in each product. And it is the same as P being a polygon with m greater or equal than 4, of course. So conjecture is, this algebraic approximation that I would like to obtain, is the following. That P is homomorphic to connected sum of sphere products with 2 spheres in each product, if and only if Kp is minimally non-Golad. And I also want it to be torsion-free. The latter means that all its induced subcomplexes have free integral homology groups. For example, in the case of Golod complex, if K is a minimal triangulation of Rp2, then K is Golod. But Zk is not a wedge of spheres. It's a wedge of spheres and wedge with suspension on Rp2, so it has torsion. The if part firstly appeared in their work as question 3.5. So here is the main theorem which I use in my consideration here. So the Tor groups from the definition of a Golod complex acquire by this result topological interpretation by means of the following result on the cohomology of that K. So cohomology algebra is isomorphic as algebra to the Tor, and the Tor can be calculated as a cohomology differential algebra of a Koszul complex. Koszul complex exterior algebra tensor Stanley-Reisner ring, Stanley-Reisner module. And these are modules of a polynomial ring, so tensor product. And by Hochster formula, or it can be independently proved using Buchstaber and Panov theorem, this is isomorphic to a direct sum of reduced cohomology of all full subcomplexes in K. Ki means restriction of K to the subset I on m variables. So this is the result. And it was additively. And what is about multiplication? So the ring structure is given by the following maps due to a result of Baskakov. This map are induced by the canonical simplicial embeddings. K on I plus j vertices lies in the join of complexes Ki and Kj. This is for I and j non-intersecting, and it is zero map otherwise. So next, let me consider some particular cases. What does this all give in the case of dual neighbourly polytopes? The definition as follows. A simple n-dimensional polytope P is called dual neighbourly if a half of its dimension vertices, or a less number, of pairwise intersection facets, not vertices because it's not a simplicial polytope, but simple one, have a non-empty common intersection. For example, of course, simplex, and moreover, a product of two simplices of the same dimension or dimension plus 1. And more interesting, duals to cyclic polytopes. So cyclic polytopes, which Nikolai introduced before me, are neighbourly ones. This can be proved using Gale diagrams, for example. The latter, these polytopes are also, like truncation polytopes, they are important in combinatorial and discrete geometry, and they are the upper bounds for the phase vectors of simplicial polytopes, not lower bounds, and then upper bounds. It was proved by Bozier and Mersmann that boundary complexes of even-dimensional dual neighbourly polytopes are torsion-free. The following statement describes the topology of Zp. So the complex is torsion-free, and we have, by Gittler and Lopez de Medrano, that if P is such, so n-dimensional dual neighbourly polytope of even dimension, then that P is diffeomorphic to a connected sum of sphere products, just our case, with two spheres in each product. And if and only if P is not a simplex, of course, we should drop this case because it's trivial. Our conjecture about algebraic characterization of connected sums relates this to the following result. In this case, if P is a dual neighbourly even-dimensional polytope, then Kp is minimally non-Golod, also if and only if P is not a simplex. In this case, Kp is Golod, not minimally non. The next case, which we considered at the beginning, is generalized truncation polytopes. In this case, for truncation polytopes P, its boundary complex is minimally non-Golod due to a result of Berglund and Jolenbeck, 2007, if P is not a simplex, of course. And we generalize it. We have in other tools, not combinatorial ones purely, but using Buchstaber and Panov theorem. And for all generalized truncation polytopes, its boundary complex Kp is minimally non-Golod if and only if R is equal to 1, so truncation polytope case, or R is equal to 2, this case when, if you remember at the beginning, Zp is diffeomorphic to connected sum of sphere products. And P, of course, is not a simplex. So what is the precise formulation? The next statement maybe is the most general fact we know about Zp topology change when a vertex truncation of a simple polytope P is performed. If for a simple n-dimensional polytope P with m facets, its moment angle manifold Zp is diffeomorphic to a connected sum of products of spheres, then the same is true for its consequent K vertex truncation for any K. It was proved by Gittler-Lopez de Medrano with one additional restriction on the number K. K plus m, so the whole number of facets of a polytope, should not be greater or equal than 3 numbers of dimension, 3n. It was technical. And recently there appeared a paper of Chinese mathematicians Chen, Fan, and Wang. They prove by similar methods and using McGovern original results and surgery techniques, this without any restriction on K. So for all K, this holds. And our conjecture relates this to the following our result. If for a simple polytope P, its boundary complex Kp is minimally non-Golod, then the same is true for all its K vertex truncation for any K. We want to generalize now vertex truncations. Consider, of course, all of you know what is connected sum of smooth manifolds. But what is a connected sum of two simple polytopes? If we have polygons, then let me describe it. If you have a polygon, triangle, and it has vertex V, and we also have, say, another triangle, and sum of its vertex W, then not precisely what we do. We cut these vertices by hyperplane, and we glue this and this simplices. It will be a simplex because polytopes are simple, and we obtain a square. So we glue it such that we should obtain convex polytope, of course. So this is equivalent to a cube, so a square. So in this case, the example which I showed is when we have P2 is equal to a simplex, then connected sum is just one vertex cut, like on my picture. And of course, if you have two polygons, also like in my picture, then the resulting polytope is, of course, a polygon with number of edges, the sum minus 2, naturally. So what is about its boundary complex, Kp, the boundary of the dual one, dual simplicial? Of course, it can be defined the connected sum of K1 and K2 in a maximal simplex sigma. So they have a common simplex of the same dimension. And what we do, we glue them along this simplex, like in my theorem about Golod complexes. And then we drop off the simplex sigma. So for example, what we have here we have also two triangles. Yes. And so this is and this is, and we glue, and so we have a one-dimensional complex. This is empty. There's nothing here. This is a boundary over 2 simplex, a boundary over 2 simplex. And so when we glue and drop this common facet sigma, then we obtain one-dimensional boundary of a square. Boundary of a square. So, yes. What is the result using the Golodness theorem and using Buchstaber and Panov theorem also, and combinatorial considerations? We have the following result about connected sums of minimally non-Golod boundary complexes. So if you have a connected sum at maximal simplex, then the result is also minimally non-Golod. And for me, very interesting open question, generalizing the result of Gitter, Lopez de Medrano, and Chinese mathematicians. Is it true that if that P1 and that P2 are homomorphic to a connected sum of sphere products, different connected sums, of course, then is it true that the connected sum of polytopes, give us the connected sum of manifolds? So also the connected sum of sphere products with 2 spheres in each product. So this is maybe non-trivial but interesting as a conjecture, of course. But what is moment angle manifold gives us? Connected sum of polytopes and connected sum in manifold in category. So simple polytopes with few vertices, with few facets, simple. So what can we say by this criterion about simple polytopes with few facets? For example, if we have n+1 facets, then it's of course a combinatorial simplex. Zp is a sphere, as we know, and Kp, as we also know, is Golod. The multiplication is trivial. So in the case n+2, then different combinatorial types of simplicial or simple polytopes are just products of simplices, 2 simplices, of course. Zp, as we know from the beginning of the talk, is a connected sum of sphere products with 2 spheres in each product. And Kp is minimally non-Golod in this case. What about n+3? This is also in combinatorial geometry. It's a case where the classification of different combinatorial types of polytopes can be obtained using Gale diagrams, Gale presentation. In this case, it follows from results of Lopez de Medrano, some early paper of 1989, that if P is not a product of 3 simplices, then that P is a connected sum of sphere products with 2 spheres in each product. And I prove the following, that for this case, m equals to n+3, the Kp boundary complex is minimally non-Golod at the same condition, if and only if P is not a product of 3 simplices, combinatorial, of course. And next case, n+4, ruins all this nice classification because it's a wild world of combinatorial types of polytopes. Of course, they depend on vertex cuts. But what is interesting, if we have a cube, 3-dimensional cube, and 1 vertex cut, then using Buchstaber and Panov theorem, of course, it was pointed out that by Mosium and Mersman in 2006, their paper on real quadrics, that P is not homotopy equivalent to a connected sum of products of any number of spheres. A homotopy equivalent is obtained because they see the cohomology ring, and the cohomology ring multiplication, it behaves not so nice, and it cannot be a connected sum of products of spheres. So the last part of my talk is about bigraded Betti numbers of simple polytopes and moment-angle manifolds. So these are the following nice numbers. This is a table of them for all simple polytopes P. They are dimensions of the components of the Tor algebra. And they are combinatorial, of course, from this definition, they are combinatorial invariants. But I think open question and very interesting is if they are topological invariants of moment-angle manifold. If you have ZP1 and ZP2 and they are topologically equivalent, what can be said about their bigraded Betti numbers? So this is an interesting and non-trivial combinatorial invariant. Is it a topological invariant? I don't know. But what we know is they behave nicely when P is not an arbitrary complex, but P is a simple polytope. Then they have bigraded Poincare duality. They obey. And they also have the following relation to the Betti numbers of moment-angle manifold. So the cohomology component is just the sum of bigraded cohomological components from Buchstaber and Panov theorem. And so the dimensions are just the sum of bigraded Betti numbers. So now in bigraded Betti numbers we can say about free part of the cohomology ring. And the following is the complete calculation of bigraded Betti numbers of all generalized truncation polytopes. So if P is an arbitrary generalized truncation polytope for all K's and all arbitrary dimensions of simplices in a product, then we have the following nice formulas for all bigraded Betti numbers, non-zero ones. So there are diagonals which are parameterized by G minus I equal to L. So these diagonals are non-zero. And the lowest and the highest diagonal, so beta minus I to I plus 1. This, of course, because of the Hochster formula, has a combinatorial meaning. And this is not on topological, because in this case cohomology groups have dimension 0, and these are just connected sums of the corresponding full subcomplexes Ki, if you remember the formula. And we obtain such nice sums of binomial coefficients. These binomial coefficients, of course, have purely combinatorial meaning, meaning if you consider the boundary complex. For truncation polytopes, so R equal to 1 and arbitrary dimension, this were calculated by Japanese mathematicians, Hibi and Terai. And for us, the crucial point of the proof is the following lemma, which can be obtained by Meyer-Vietor's principle. So let P be generalized truncation polytope just defined above. K its boundary complex, V the vertex set, and W is some non-empty but proper subset of V. Then we have the following. Mostly its homology or cohomology groups are trivial, but for some i's positive, which are subsets, which are subsums of powers, this is non-trivial and equal to K. And if and only if W is a join of some vertex sets of a simplex added by some new vertices. New vertices means in a simplicial polytope. So in a simple polytope you perform vertex cuts, and in a simplicial polytope you obtain pyramids over facets. These pyramids have vertices, these are new vertices, and we have such a presentation. These are the most important references. And the last but not the least. Thank you very much.